Hi, and welcome to Aerohive's Introduction to 802.11n. My name is Devin Aiken, Devinator for short. The 802.11 standard is an IEEE document describing the technical details of Wi-Fi technology. When you add the standard to the currently ratified amendments, you're looking at over 2,000 pages of technical jargon that reads like federal tax code. The 802.11n amendment covers enhancements to the physical layer, that is radio frequency, and the media access control layer, that is the direct connectivity. The physical layer is often referred to as the PHY, and the media access control sublayer is often referred to as the MAC. A term you may have heard already relating to 802.11n is MIMO, which stands for multiple input, multiple output. MIMO is the capability to use multiple transmitters and receivers simultaneously. Prior to MIMO, we had SISO, that is single input, single output. SISO systems were limited in many ways, which is what makes MIMO so exciting. Can't you tell that I'm excited? 802.11n gives users a much better experience for data, voice, and video. In real-world environments, throughput can reach levels 5 times higher than in existing 802.11ag networks due to higher data rate support. 802.11n offers consistent and predictable coverage and throughput because it takes advantage of multipath rather than being hindered by it like 802.11abg networks. 802.11n infrastructure offers much better rate over range, which is a tidy way of saying that you can still get high throughput when you're a long way from your servicing AP. 802.11ag networks tend to have a steep data rate fall off as the client ventures away from the AP, but due to the advantages of MIMO technology, 802.11n doesn't suffer nearly as much from this problem. 802.11n devices offer backward compatibility with 802.11abg devices in both the 2.4 GHz ISM and 5 GHz unibands. This assures that the user's previous hardware investment is not wasted. Spectral efficiency is significantly better with 802.11n, which means that while using the same 20 MHz channel space, an 802.11n connection may have almost 3 times the throughput of an 802.11a or 802.11g connection. This spectral efficiency stems from a series of new PHY and MAC layer features that we'll discuss shortly. Backward compatibility means that you can upgrade your network from 802.11a or BG to 802.11n a step at a time, where both technologies exist in your network simultaneously. With multiple receivers and transmitters and an incredible new upgrade called a digital signal processor or DSP, radio frequency communication is handled much more reliably. If the physical layer is handled better, then MAC and IP layer quality of service or QoS mechanisms placed on top of the PHY will work much better. By stabilizing the PHY, we get an n-fold increase in QoS performance. Modulation encoding schemes, called MCSs, are fancy new names for data rates. We use MCS now instead of data rate because there are so many variables that factor into the speed at which a client and AP communicate. These variables are comprised into sets called MCSs, and current equipment support MCS rates of up to 300 megabits per second. Data throughput of over 200 megabits per second is now possible due to 802.11n's massive protocol efficiency improvements. With greater range due to improved protocols and use of multiple radios, an 802.11n deployment doesn't typically require as many APs to cover a given facility at a given MCS rate. With the additional predictability and reliability offered by 802.11n, your voice and video applications will function just as they did when connected to an Ethernet cable. Multipath problems will no longer be a major source of frustration during your network design phase, because multipath, that is the effect of having multiple copies of a single transmission, helps the DSP at the receiver to differentiate between simultaneous transmissions called spatial streams. We'll talk about spatial streams in another tutorial. To sum it up, 802.11n is technically better than 802.11a, b, and g in every way. The data rate for 802.11a and g peak at 54 megabits per second, yielding up to 26 megabits in actual throughput. Of course, the throughput is dependent on such parameters as how many devices are associated with the AP, what type of data is being transmitted by each device, the distances of each device from the AP, and nearby interference sources. Considering the 300 megabit per second data rates currently available, throughput of over 200 megabits per radio is possible using 40 megahertz channels, short guard intervals, multiple spatial streams, aggregate frames, block acknowledgements, HTOFDM, and several other mechanisms Many 802.11n APs have at least two radios, so for each radio in the AP you should consider at least 200 megabits of throughput capability for the backhaul Ethernet link. 802.11n has its own PHY layer, which uses a new form of OFDM modulation called high throughput OFDM or HT-OFDM. We'll talk a little more about HT-OFDM in another tutorial. 802.11n helps network designers overcome challenges in a variety of ways. In environments such as manufacturing facilities, warehouses, and on factory floors, multipath problems can be overwhelming to the point where Wi-Fi systems perform very poorly and some applications may not work at all. MIMO technology uses multipath to its advantage, so RF environments that we used to consider harsh are now quite easy to accommodate. Another major challenge is that of bandwidth, or you might say throughput. 802.11a and G systems gave us no more than 26 megabits per second, and in some cases much less. When moving from fast Ethernet or gigabit Ethernet to 802.11ag, the ability to move very large files across the network suddenly vanished. 802.11n gives us speeds higher than fast Ethernet by using multiple spatial streams, that is, multiple simultaneous transmissions, 40 megahertz channel widths instead of 20 megahertz channel widths, and frame aggregation with block acknowledgement, just to name a few. Whether you're moving digital medical images, uploading CAD files, or just doing basic file sharing, 802.11n is a breath of fresh air. High throughput is a networking requirement in a number of vertical markets such as healthcare, engineering, and education. Faster is always better, and soon we'll have 450 megabits per second MCS rates available. That will mean peak throughput levels of over 300 megabits per second across the wireless medium. 802.11ag networks were riddled with coverage consistency and latency problems, and achieving a wire-like application experience over 802.11ag was next to impossible in all but the best RF environments. Through superior RF handling, more consistent coverage, and efficiency and reliability enhancements, 802.11n offers a more consistent application experience, especially for latency-sensitive applications in vertical markets such as healthcare, retail, and warehousing. In environments where users are allowed to bring any type of Wi-Fi-enabled client device, compatibility and high performance is a serious challenge. In several industries, such as hotspots, hospitality, and education, having a wide variety of client types connecting to the Wi-Fi infrastructure is the norm. By supporting all prevalent Wi-Fi connectivity standards and maximizing the throughput and coverage of each type, 802.11n is in a position to offer much better customer experience in several vertical markets. The hardware used in an 802.11n network is quite a bit more sophisticated than its 802.11abg predecessors. Instead of the single radio chain, that is, a single radio and antenna paired together, that was used in 802.11abg networks, 802.11n uses multiple radio chains together as a cohesive unit. The left side of the slide represents a physical 802.11n radio card. There are several types of 802.11n radio cards, but this one represents a 3x3 radio card housing 3 transceivers. A transceiver is a single radio chain capable of transmitting or receiving, but not at the same time. Notice that each radio is connected to an antenna, forming a radio chain. Each of the radios is connected to a digital signal processor, or DSP, which in turn connects to the Wi-Fi chipset called a baseband PHY and MAC processor. The baseband processor connects to the bus, which could be mini PCI, mini PCIe, card bus, USB, and others. For most access points, the radio chains are dual band, meaning they can transmit and receive in 2.4 or 5 gigahertz. Enterprise class APs generally contain 2 radio cards, meaning 6 radio chains, 3 operating on each band. A client station, if it's using a 3x3 radio, will also contain 3 radio chains, which can be used either on 2.4 or 5 gigahertz, but not both simultaneously. The DSP is responsible for performing all types of tricky protocol maneuvers, such as splitting a data stream into multiple spatial streams and collecting multiple copies of the same signal from the wireless medium and putting them all back together into one easy-to-understand signal for the baseband processor to process.